We just saw the Burrows-Wheeler transform and we saw how it can be thought of as a compression booster, but we have some pending problems that we need to solve. One of them is that we need to know how to reverse the Burrows-Wheeler transform to get back the original text T when all we have is the Burrows-Wheeler transformed permuted text. So that's what this lecture is about. And another thing that we'll have to tackle is how we do these things efficiently. That will be tackled in future videos. Okay, so the question we're tackling here is how to reverse the Burrows-Wheeler transform. We saw how to do the Burrows-Wheeler transform in the forward direction, right, where we take our string, we sort all of its rotations to form the Burrows-Wheeler matrix, we take the final column. That's a permutation of the original text. Specifically, it's the Burrows-Wheeler transform. But how do we go backward? That's harder to see. Okay, so let's start with a kind of notational point that will help us to track different occurrences of the same character as we talk through how to undo this permutation. So we're going to give each character in our string T a rank according to, for that character, how many times did that character occur previously in the string. Or another way of thinking of it is, for the A's, we're going to go left to right and give them ascending ranks, 0, 1, 2, 3, 4. Same thing with B's, same thing with all the other characters of the alphabet. So with this particular string, what that means, we're starting over here at the left. This is the first A. That's the first A, so we're going to give it a subscript of 0, a rank of 0. So I'll draw the rank in as a subscript. So sometimes I'll call them ranks, sometimes I'll call them subscripts. All right, so there's the A of rank 0. Now I'm looking at this B. That's the first B, so it's the B of rank 0. Right? There's no B's previous to that one. Okay, now I'm on the next A. That's the A of rank 1, since there's one A previously. Now I'm on to the next A. That's the A of rank 2, since there are 2 previous A's. This is the B of rank 1. This is the A of rank 3. And there's no point giving the $sign a rank. There's always only one $sign, so I could give the $sign a rank of 0, but for simplicity, I'm just going to not give it a rank at all. Okay, so there's my string T now with the characters in the string ranked. Now I want to emphasize we're adding these ranks purely so that we can visually easily distinguish between the different occurrences of the different characters. I'm not saying that ranks are explicitly stored. So I'm not saying, for example, that the Burrows-Wheeler transform string or that the Burrows-Wheeler matrix needs to be accompanied by another array or another matrix of ranks. Right? No, we're not going to explicitly store them. But when we draw the pictures for this video, we are going to draw the ranks. We're going to draw the subscripts so that we visually can easily distinguish the different occurrences. Okay? So with this convention, now let's just write out the Burrows-Wheeler matrix again, but with the ranks included. Here we are. So same old Burrows-Wheeler matrix as before. All right, all the black part is exactly the same. All that's new is that now the characters, except for $sign, have subscripts, which are their ranks. Okay. So like, we can just look across one of the rows. I could pick the first one, but that one's maybe a little trivial. So let's go down to this row, for example. Starting after the $sign, we can see this is the leftmost character of the original string. So it's the A of rank 0, B of rank 0, A of rank 1, A of rank 2, B of rank 1, A of rank 3. Makes sense, right? Okay. Now I'd like to cut out part of this picture, sort of just cover it up. I want to cover up everything except for the first column and the last column. We already know the last column is special, right? We already gave the last column a name. We called it the BWT of T. So we know the last column is special. The first column, it's hard to think of it as being very special, right? Because it has this, I guess it's special in the sense that it has this very predictable structure where there's always going to, first of all, there's always going to be a $sign first, right? That's a guarantee because the $sign is defined to be alphabetically less than all the other characters. So of course the rotation that starts with the dollar sign must be the first in when we alphabetically ordered the rows. So that comes first, no question there. Then whatever the next highest alphabetical character is, A in this case, there's going to be a bunch of rows that start with that letter. And then whatever the next highest alphabetical character is, there's going to be a bunch of rows that start with that letter. It's going to be very predictable. It's going to be dollar sign, and then in ascending order, blocks of rows starting with each character of the alphabet. Okay, for all the characters that are present in the string. So it's kind of a predictable looking column. The first column we know, as soon as we know how many times each character occurs, we know exactly what the first column is going to be. But it's going to be important for what we discuss next. So we're going to say, let's keep this and let's keep this, and let's just imagine for a moment that we are throwing out everything else. And by the way, in practice, you do indeed throw out everything else. You know, there are some auxiliary data structures that we'll keep, but we don't keep the entire Burrows-Wheeler matrix. That would be far too big in practice. Okay, so we just want to look at the first and last columns here. And let's start by narrowing our focus even more to just the A's in the first column and the A's in the last column. Okay, so we've got just the A's here. Now notice something about the A's. Let's go from the top down in the first column. We see A of rank 3, A of rank 1, A of rank 2, A of rank 0. And now as we go down the last column, we see A of rank 3, A of rank 1, A of rank 2, A of rank 0. It's the same pattern, 3, 1, 2, 0. 3, 1, 2, 0. So they're all together here and they're spaced out here, but it's the same order in both cases. 3, 1, 2, 0, 3, 1, 2, 0. So here we go. The A's occur in the same order in the first column and the last column, right? They're all A's, but we added the subscripts, so now we can distinguish the particular occurrences of A, and it turns out it's the same order of those particular occurrences in F and in L. Okay, let's look at the B's. Same thing, right? As we look down the first column, we see rank 1, rank 0, and as we look down the last column, we see rank 1, rank 0. So it's also the case with the B's. And indeed, it's true in general. And this is called the LF mapping property. It's a special property that the Burrows-Wheeler matrix has, and it unlocks a lot of the things we'd like to be able to do with the Burrows-Wheeler transform. And the first one we'll see is it allows us to reverse the Burrows-Wheeler transform. Okay, so let's state this LF mapping property. The ith occurrence of some character C in the last column, L, and the ith occurrence of that same character C in the first column correspond to the same occurrence in the original text T. In other words, they have the same rank. Okay? So, you know, let's do this again for the A's. Let's just pick let's say when we say ith occurrence, let's say we're talking about the second one down, just as an example. So the second A down in the last column is this one, and it has rank 1, and the second A down in the first column is this one, and it also has rank 1. That's what the LF mapping property is telling us. They're going to have the same rank. Now let's try the fourth one down. Okay, 1, 2, 3, 4. That has rank 0. 1, 2, 3, 4. That has rank 0. That's what the property is saying, is that if you go to a particular occurrence of a character in the last column and same character in the first column, you'll find they have the same rank always. That's a general property. Okay? So that is, we'll see in a few slides how we can use this property to help us to reverse the Burrows-Wheeler transform. But first, let's see why that's true. Right? We can see pretty easily and intuitively why this LF mapping property holds. So let's take a look. And let's do it by, I've got the Burrows-Wheeler matrix here twice, okay? And I didn't bother to give ranks to the characters in the middle because I'm asking you to imagine that we're not even keeping anything but the first column and the last column, okay? And so we want to ask this question, why does the LF mapping hold? So let's start with a more specific question, which is, why are these A's here in the first column? Why are these A's in this relative order? Why do we get this order where it's A3, A1, A2, A0? What's causing them to be in that order? Well, it's not the A itself, right? The A itself is the same, right? They're all tied with respect to their initial A, right? So that's not why they're in that relative order. They're in that relative order because of these, because of the sequences that come to their right in the Burrows-Wheeler matrix, or in other words, by their right context, right? So those A's, boom, 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 those A's are in that order because of the order of their right contexts. Okay? They're not in that order because of the A's themselves, because it's a tie, right? So that doesn't really determine their order. They're in that order because of these, right? Okay? There you go. So the A's are in that relative order because of their right context. And now we can ask the same question about the A's as they occur in the last column. So why are these A's in this order, in this relative order? Well, it's because of what comes here, right? What comes to their left in the Burrows-Wheeler matrix. But rotationally, what comes to their left in the Burrows-Wheeler matrix is their right context, right? So they're in that relative order because they're sorted by their right context with respect to the original string. Same reason. That's why the LF mapping property holds. If you just fix your attention on a particular character, like we did with A in this example, and think about why are those A's in that relative order in the first column? Well, it's because they're sorted by their right context. Then you look at the last column and ask the same question. Why are those A's in that relative order in the last column? It's because they're sorted by their right context. Same principle, same reason. Therefore, they'll be in the same order. Therefore, the LF mapping property holds. Okay, so occurrences of some characters C and F are sorted by their right context. Same for L. That's the intuition behind the LF mapping property. Okay, so equipped with the LF mapping property, let's reverse a Burrows-Wheeler transformed string. Okay, so I've got my string T here, but you have to imagine we actually can't really see that. I'm just drawing it here for clarity, for the illustration. Imagine all we have is L and F. So L being the Burrows-Wheeler transform string, right? L is just another name for the Burrows-Wheeler transform of T, okay? And we've got F, which again has that very predictable structure, right? As long as we know the number of occurrences of each of the alphabet characters, we know exactly what F's going to look like. It's going to have this block structure. Okay? So we're going to try to reverse the BWT starting at the right end of T, right? The dollar sign, in other words, and going kind of backwards. We're going to start at the end and reconstruct T, but going backwards. Like this. Boom, 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 boom. Okay? And we're going to start in the first row. We're going to start in the first row. We always know that the first row starts with dollar sign. It's a guarantee because we define dollar sign to be less than all the other characters. So once we put the rows in alphabetical order, we know the row that starts with dollar sign must come first. And so if the row with dollar sign must come first, that tells us something about the first character in the Burrows-Wheeler transform. It tells us that the first character in the Burrows-Wheeler transform, right, this one, the first character in the Burrows-Wheeler transform is the one that comes just before the dollar sign. This one. Right? We know that that character must be in the first position of the Burrows-Wheeler transform because if the dollar sign is here in the first column, then rotationally, this is the thing that comes just to its left in the original string. Right? This is the thing that comes just to the left of that. Okay? So we've actually made a little progress, right? So we actually now have kind of reconstructed the character that comes just to the left of the dollar sign. Okay? All right? So if we start in the first row, we know that F must have a $sign in that first row, because $sign is alphabetically first. And therefore, the corresponding character in L, the first character in L, is the one that comes just prior, which is the A of rank 3. The next trick, which is where we use the LF mapping property, is that we want to jump to the, we're going to iterate. We want the next iteration, we want to jump to the row that starts with the A of rank 3, right? The first row is the row that ends in the A of rank 3. Bloop. Now we want to jump to the row that starts with the A of rank 3. Okay? So what do? We use the LF mapping principle, right? This is the A of rank 3. It's the first A in the last column, right? The other A's are down here. It's the first A in the last column. So which is the row that has the A of rank 3 at the beginning? Well, it's the first A. Okay? So where's the first A? Well, it's right after the $sign, right? This is always going to have this block structure. $sign, and then all the A's, and then all the B's, right? So if I want to jump to the row that starts with the A of rank 3, I kind of know where to go. I want to go to the first slot in the A section. All right, so if I could do that, then that would tell me which row I should go to next. So if I jump to the row beginning with the A of rank 3, I can simply repeat what I did in the first row, which is I can now ask, well, what's in the last column in that row? Because that's the character that comes just prior to the A of rank 3, which is the B of rank 1. So we've now reconstructed one more character going to the left from the $sign. Okay? All right? And I can repeat. Okay, so now I'm in the row I just finished just now, and in the row that ends with the B of rank 1. Now I want to jump to the row that begins with the B of rank 1. Well, the B of rank 1 is the first B, right? It's before this one. The B of rank 1 is the first B in the L column, so I need to jump to the first B in the F column. All right, which is going to be after the group of, after the $sign and after the group of A's, right there. That tells me where I should be for the next iteration. So what do? I look in the last column of that row, and I see the A of rank 2. So I know, moving to the left from the $sign, the next character to the left is the A of rank 2. Okay? And I just keep repeating. All right, so here I am in the row that ends with the A of rank 2. I want to jump to the row that begins with the A of rank 2. The A of rank 2 is the 1, 2, it's the third A. So I'm going to jump to the third A in the first column. There I go. Then I'm going to jump to the character in the last column corresponding to A of rank 2. I got the A of rank 1. That's the next character to the left. Let's keep going. A of rank 1 is the second A, so let me jump to the row that starts with the second A. Jump over here. I see the B of rank 0. There we go. B of rank 0 is the second B, so I'm going to jump to the row that starts with the second B. Great. I'm going to jump to the last column. I see the A of rank 0. That gets me here. I probably know the length of T, in which case I know that I'm done now, right? I've recreated the $sign and everything that comes before, but even if I wasn't keeping track of the length of T, I would quickly discover that I was done, right? Because now I'm in the row that has the A of rank 0. That's the fourth A. So next I would jump to the row that begins with the fourth A. That row. Look over here, and what do I see? I see the $sign, right? So if I didn't already know that I was done, then a big hint is that I see the $sign, right? So if I see the $sign, I know I've wrapped around, so I must be done. Okay? Etc. So I just repeated this process until I got all the characters of the string T, and I got them backwards, going backwards from the $sign. Right, I started at the $sign, and by repeatedly applying the LF mapping and then going and looking in the last column of the row that I jumped to, that allowed me to reconstruct this sequence of characters backwards and reconstruct T. So there you go. That's how you recreate the original string given the Burrows-Wheeler Transform string, and the main principle it's using is this LF mapping property.